Okay, so one thing that a lot of groups were faced with during the first reaction was trying to understand what was going on with the TLC of their reaction, right? So, what was the observation that we made with the TLC of the first reaction of the sequence that we've been working through? What do we expect to happen on the TLC?
The minor product traveling fractionally further than the major product.
Yeah, so when it goes all the way to product, you expect a minor product, and we knew that from the beginning because I gave you an example, TLC in a notebook that someone else did, right? You had a starting material that was down here at some polarity, and then at the end you would have like a minor product that travels slightly further, and then a major product somewhere below it, right? That's what you expect. But a lot of people got confused. This is what you would expect to see if, if what? Like, what would you use to visualize that, to see that picture?
A UV lamp.
A UV lamp, that's true. Would that be the same picture or a different picture if you stained it with phospholytic acid? Is it the same?
It should be.
Yeah, so what some people observed was when they would get their UV, that's what it would look like, and when they would stain it, they would see another big spot right there. Right? So this one, the ones that I've colored in, those only showed up with the stain. Right?
Mm-hmm.
And the question is, why is that? Why is it that these products, they showed up under UV light, and the starting material showed up under UV light, but the, what do we call that thing?
Intermediate.
That's an intermediate, right? That's some intermediate that forms, but we don't see it under UV light. So some groups were actually tricked. If they didn't stain it, they would think the reaction was done, but actually a lot of the stuff was the intermediate, right? See what I'm talking about? So you can trick yourself unless you are aware that you're making an intermediate. So what is it that determines whether we see a compound under UV light? What is it? What structural characteristics determine whether a compound can be visualized under UV light? Does anyone have any ideas? Has anyone ever talked to you about it before? I'm asking. I'm trying to probe your knowledge base.
Not really.
So there's a structural difference. So when we look at these compounds, this is the starting material, the pyrone. Okay, and it can be visualized under UV light. It goes this reaction, right? There's this palladium chemistry, and then there's this short-lived compound C that goes to D, and that's the intermediate. How do I know that this is short-lived and then that's an intermediate? Like, they're both intermediates, but one C is very short-lived. D is much more stable. In fact, you can isolate D.
There's not a charge.
Yeah, it's not charged. Like, you get the idea that this is unstable. You've got an oxy cation right there, right? An oxonium ion. So oxonium ions are unstable. Oxygen is like to bear a positive charge. So this is a highly energetic species, and it's going to be more stable once the methoxide attacks. Methoxide itself is also a strong base, and it's unstable until it attacks. So D is this intermediate we're talking about. So we have something that's UV active, a starting material, that goes to something that's not UV active but stains, and then when the second cycle of the reaction occurs, this is our product over here. It's drawn in a different way than we usually draw it, but that's the product, and again, it's UV active. Does everyone see that? It's UV active, and there's a major and a minor depending on, the geometry around that double bond, right? But they're both UV active. So can anyone pick up on the big difference? Like, what's different about this one and that one compared to this one? Does anyone see the structural distinction between those three compounds? Think about it for a minute. Talk to your neighbors. This is a specific example of a general phenomenon. So we're going to talk about the general phenomenon in a minute, but you've been dealing with this particular case. what does the starting material in the product have that the intermediate doesn't? Structurally.
They have double bonds near each other.
Oh, how near each other? Like, describe the relationship. I think Lawrence is onto it.
I don't know
What
if
is
would
that?
that be classed as vicinal? Like that double bond and the other one. There's
What do we call this relationship where we have a double bond, a single bond, and a double bond? What do we call those?
diene.
It's a diene, but specifically what kind of diene? Conjugated. They're conjugated. So when you have conjugated pi bonds, compounds tend to be more UV active, right? So notice that's true in the starting material. We've got conjugated double bonds. We've got this, in fact, we have this carbonyl, which is conjugated to this double bond, which is conjugated. So this is an alpha, beta, gamma, delta unsaturated lactone. So it's got lots of conjugation. 3 pi bonds separated by single bonds. See that? Notice in the intermediate, all that conjugation is broken up. There is no conjugation. You have, if you count the esters, you have, 4 isolated double bonds. Okay? They're isolated. They're not conjugated, meaning it doesn't go double, single, double. Right? They're isolated. They're separated by at least 2 sp3 hybridized carbons. And then in the product, again, we have a conjugated system, right? You've got that CO2Me, that's an ester, right? So that's another situation where you have a double bond conjugated to another double bond conjugated to another double bond, right? So we have an alpha, beta, gamma, delta unsaturated ester again. So those compounds are UV active. So this is a general phenomenon. When you have conjugated double bonds, you tend to see compounds absorb UV light, which makes them chromophores. Okay, and so I've got a little handout about chromophores, which I derived from another class that I taught that had more to do with this, but this is a useful thing. So I'm going to hand this out and let you guys have a read of it. And I don't know that it's important that you do the practice, but there's some practice there. And the key is already linked online, so if you want to look at the key, you can see the key. So when you're looking at a reaction for the first time, and you're thinking about how to visualize a TLC, one thing you look for is conjugation or aromatic rings in the starting materials or the products, right? So if you're working with an unfamiliar reaction, you're trying to think about how best to visualize it, you have to pick the right technique. UV light works really well if you have conjugated double bonds. It doesn't work at all if you don't, right? So that's kind of the purpose and the point. So I'm going to hand this out, and then we're going to talk just a little bit about why that is, and then I'll turn you loose to read it if you like, and get whatever else out of it you want to. So is Nicole coming back? Should I give her a handout?
Yes.
Yeah. These handouts are all linked to the Moodle page, too. So have you heard of these concepts, highest occupied molecular orbital and lowest unoccupied molecular orbital, the HOMO and the LUMO? Have you heard those terms? Nod if you have, because I'd like to know. So, Jess, is that a yes or a no, or is that a maybe?
I don't remember it, but I may have been supposed to know them.
You might have heard about it in the past, but it's
Yeah.
a little fuzzy.
I'm in the
So,
same boat.
Okay, great.
how about you in the back? Heard of
I've heard it before, but a while ago.
Okay, so what we're talking about here is we're talking about molecular orbitals. So most people who have had a bit of chemistry remember the atomic orbitals and the atomic orbital filling. When you're talking about electron configuration, say, of something like lithium, right? You would say it's how do you name its electron configuration?
1s2.
1s2, 2s1, right? And that would get us to lithium, right? And so what do those letters mean?
The type of molecular orbital.
Well, these are atoms, so
Atomic orbital.
the type of atomic orbital. So we remember, atoms have a set of orbitals, hydrogen-like orbitals, that fill from lowest energy to highest energy, and you place electrons in the next lowest available energy one until you get to the number of electrons that particular atom has, or that ion has, right? So you fill up. So those orbitals are shapes in space. They're energies and they're shapes in space that electrons can occupy. when you're talking about molecules, molecules have the same kind of fine structure as atoms do, except the electrons are spread out over the whole molecule. And so again, for every pair of electrons, there's an energy level into which they fill. We call those molecular orbitals. They're not shaped like the atomic orbital ones, like the S is not a sphere, right? There's no S orbital for molecular orbital. And like, you know what, the P's look like this in atomic orbitals. There's no corresponding isolated p orbital. We're talking about molecules, so the electrons spread out over the whole molecule, and those molecular orbital shapes get very interesting and complicated. But when you're dealing with pi bonds, and that relates to our topic today, you can describe the bonding in a pi bond as just kind of ignoring all of the other electrons except the ones in the pi bond, because the pi bond is where the highest energy electrons tend to be. So the orbitals that are responsible for that. And a pi bond forms by the combination of two p atomic orbitals. So if this is an atomic orbital and this is an atomic orbital, a pi bond forms when those two atomic orbitals come together in phase. And what I mean by in phase is when they come together in phase like this, there's constructive interference, and the electron density kind of smears out above and below the interatomic axis, right? And so this whole area is occupied by electrons, and that whole area is occupied by the two electrons that are in that orbital. And then there's a corresponding anti-bonding pair where there's destructive interference between the two. And the way I have it illustrated is relative to the energy of the orbital, right? So you have these two combinations. This is the bonding molecular orbital. That's where the two pi electrons go. Usually every atomic orbital brings one electron in with it. So these two electrons that came in will pair up and occupy this region of space. And this one will be empty. It will be a virtual orbital. Okay, so what that means, if we look at this in terms of an energy level diagram, we've got the molecular orbital here, that's the bonding one, and then we always call it molecular orbital star as the antibonding one. And so these are pi orbitals, so I'll call it a pi and a pi star molecular orbital. And there are two electrons in the pi molecular orbital. That's what the pi bond is. This is forming a more stable pair. The atomic orbitals would have energies here and here. They each bring one electron with them. They pair up into the pi molecular orbital. That's what the pi bond is. Now, if you take light and you shine it on a molecule that has a pi bond, if the light has enough energy, it will promote one of these electrons from this pi molecular orbital, which is the highest occupied molecular orbital in the molecule, to this orbital, which is the lowest unoccupied molecular orbital. And so if the light has the right energy, it will promote one electron up. That's the absorption of light. The frequency of that absorbed light has to do with the difference in energy, this delta E. Delta E equals h nu. So that will determine the frequency or the wavelength of the light that is absorbed. When you're talking about an isolated pi bond, that energy gap is in the X-ray range. X-rays. So that's the reason why this intermediate doesn't absorb UV light. We can't use a UV lamp to visualize it because the light that would be needed to excite those pi bonds is in the X-ray range for isolated pi bonds. So no UV light, no visible light. Those compounds will appear clear to us even if we can see in the UV. If you look at the paper that I put in front of you, it sort of illustrated this diagram that I just showed you. The energy difference for an isolated pi bond in ethene is on the left, and it sort of shows you there's an energy gap. It's about 690 kilojoules per mole. That corresponds to X-ray light. It's a very high energy light. However, what happens when you start conjugating pi bonds is you get another picture. It's more complicated because the pi bonds are now conjugated. So if you have two atomic orbitals coming together, you make two molecular orbitals in ethene. But if you have four atomic orbitals coming together to make the butadiene case, notice you have four molecular orbitals there. You have four electrons to fill, so the HOMO-LUMO gap then is between the second one from the bottom and then the lowest unoccupied is the one just above the dotted line there. The important thing to notice is that the HOMO and the LUMO get closer in energy the more conjugation there is. And so even if you add one pi bond, that's enough to get that energy gap into the UV. As it turns out, for butadiene, the simplest of the conjugated systems, that energy gap is 545 kilojoules per mole. That corresponds to 214 nanometer light, about 214 to 218 nanometer light. Okay? That energy gap is in the hard UV. So that's something you could see with a UV lamp. Is everyone with me? So as soon as you add conjugation, then you start to see UV activity. So we call those things that have absorbed UV or visible light, we call those things chromophores. Is everyone with me? So that's sort of the physics reason behind why we can't see D using UV light, but we can stain it, because that just involves burning the compound up. We oxidize it and it turns black. We can both burn and see the starting material, and we can both burn and see under UV light the products. Yeah, everyone with me? So again, this is all just to sort of justify why different compounds behave differently under UV light. So what I've included here is way more than what would be required, but for this lab. But it's kind of fun anyway. R.B. Woodward, a very famous organic chemist, came up with a set of rules that would allow you not only to predict whether a compound does absorb UV light, but actually the wavelength of light that it absorbs. And they're called the Woodward rules. And this little handout teaches you how to use the Woodward rules to predict the UV absorbance of particular compounds. And all the tools you need are right here on this page. So the process goes like this. If you want to turn to the second page there, it says Guide to Identifying Chromophores. The first thing you do is you kind of identify what kind of conjugated system you have. You've got sort of heteroannular dienes, where there's a double bond within a ring and a double bond outside, or no ring at all. Then you have homoannular dienes, where both the double bonds are within the ring. And then you have alpha-beta unsaturated carbonyl compounds. So they all have different base wavelengths. That's the wavelength you start with, and then you make adjustments to it depending on what's bound to the chromophore. And the table on the back gives you the guide. So you start with your base wavelength, and then if there are substituents in different places, you add or subtract wavelength, and you can come up with a very accurate prediction of the wavelength that a compound will absorb. I'm never going to ask you to do this on an exam. It's just kind of fun to know that you can do that. You can just look at a structure and predict the wavelength. This is all empirical. It's not theoretical. It's an empirically derived system. So anyway, that's all I wanted to say about UV activity. I was surprised last year at this stage that students weren't already aware of how to know when compounds are UV active or not. So I thought I might share it with you. So that's all I've got. Lawrence, will you stop, or Justin, stop there?
How does one stop?
Just go to the little camera and say stop.
Oh.